So last week we were talking about the autoencoder. So if you recall, it looks like this one. We have an encoder right here, an encoder, and we have our X as an input, and after it works through the encoder, we get a latent or a code maybe called Z or H, and when we use the decoder right here, and we get an X prime as an output. So usually, our goal is to have that X prime is very close to or ideally equal to X. Because we wish to make this model on this encoder and decoder more interesting, so usually we will have Z to be has a smaller dimension, like if Z to have a really big dimension, this might be too easy because you know that an identity matrix can do the same. 好，所以我们通常这边的话进来的话，一个 encoder 让你 x 进来会得到一个 z 一个 code 或 latent， 然后一个 decoder 得到 x prime。我们的目标是要 x 跟 x prime 相等，这之前的。然后当然一个重点是这个 z 的 dimension 要比 x 要小很多，不然的话这些问题会太简单。However, although this can be viewed as a generative model, if in a sense that by given any latent code z, we can construct some x back. Work like this one, d, z. So by changing the z, and we can generate samples similar to our original distribution x. Because by varying the latent code z right here, we can get something similar to what we were training this model, that is the distribution x. 所以如果我们把这 z 丢到 decoder， 我们只看 decoder 的话，它看起来就有点像是一个 generative model. The only problem is that we don't know what the space or the distribution of z is, because the distribution of z is dependent on x. So although we may have some idea of what the z is, but if you just use a random distribution like a normal distribution or like other uniform distribution or other predefined distribution or any non-distribution, the generated things may not be the same distribution as x, and in practice, it may be very far off the distribution of x. 好，所以问题只是在这边，就是因为我们不知道 z 它的真正的 distribution 长什么样子，它的 distribution 应该长得像是 ex 的样子。这边 e 指的是这个 encoder， 那 x 跟资料有关，只是我们的 x 我们没有全部的 x， 我们只有那个data set， 所以我们其实不晓得 z 它应该是什么样的 distribution。那你可能说好，我随便找一个像是 normal 啊什么东西丢进去就可以了。那常常这件事情因为不可控制，然后当然你还是可以生出一些东西啦，但是它可能跟原来我们想要的 x 那种 distribution 就长得不一样。好，所以this makes some issues. Variational autoencoder can kind of can be viewed as a technique that can solve these issues by training an autoencoder. However, along with that, we can assume this distribution to be normal, this distribution to be normal, like a regular normal distribution. So instead of just rely on the training procedure and hoping this z to be to have a good behavior or have some good distribution, instead we actually introduce a loss function in our objective so that z will very close. I mean, theoretically, it will become the standard normal distribution。所以 variation AutoEncoders 可以看成是一个解法，它的关键其实就是在于它引入了一个 loss。除了原本你可以这样看啊，除了原本的这个 x 跟 x prime 可能我们希望 x。So one loss is something like we want x and x prime to be pretty. This is a mean square error to be really small, and we also want this distribution like EZ be very close to. Let me rewrite it again. Okay. So our objective is something like, okay, we want our x and minus decoder and encoder x is to be really small. And we want EX, the distribution of EX, I consider this as a distribution. It is really close to, this is normal distribution, 0, I. Where I is the identity matrix, 1, 1, 1 on a diagonal and 0, 0 otherwise. This is the identity matrix. I is the identity matrix, which means it is simple. Okay, because if you are not familiar with the notations of like normal distribution, you may think, oh, we got a bunch of variables like n stands for normal distribution. That sounds okay, but what does it mean by I? Actually, I means simple. They are trying to send you a message like, okay, I'm not going to make the things complicated. I'm just trying to use the simplest, the most simple model as possible。所以这边这个 I 其实它传达的讯息是，我现在要模型是简单的它已经告诉你是简单的。那如果你看不懂的话，你会觉得好像都是符号很复杂，但是我们最后希望的东西其实是简单。这个简单是什么呢？我们其实就是常态分布，而且呢比方说我们要生的是图片的话，每一个它的 component 或者每一个 pixel 向量的话就是每一个 component， 图片的话就是每一个 pixel 它都是一个独立的因为你看这个只有对角线上有1嘛，其他都是0，其他都是0代表了没有 correlation 没有那个 covariate 就是两之间它的那个每个 pixel 和每个 pixel 之间他们没有什么关系，我们不用考虑他们之间关系，他们是独立生的。所以这个是一个很简单、很单纯的一个就最简单的一个常态分布。So this is the most simple distribution, normal distribution as possible for like an n-dimensional one. So every component is independent. So we can just simply, no matter how large the dimension is, we can simply generate each of the component separately and independently. 所以事实上就是一堆小小的，你如果知道一维的 normal distribution 是什么，它的每一个 pixel， 它这边讲的很单纯，这个 I 其实告诉你就是我们每一个东西就独立去生，不管它的维度有多大，我们每一个地方就是反正就是随机生出一个常态分布的东西出来，而且它是标准常态分布and it is a standard normal distribution that is the mean is 0 and the standard deviation is 1. So every element is an independent random variable, which is good, which is simple because no correlations or no covariance between each of the element, and everyone is the same, is identical, which is something we call the IID, independent identical distribution. This is a simple case. Okay, So we have two rows. I mean, it turns out we are going to have something like a mean square error, like an autoencoder, and we're going to introduce another laws that to make sure this distribution, like the z, is similar or very close to a standard normal distribution. So what is this loss? This is something related to the KL diversion, which is a uh, common loss function or matrix to measure the differences between two random distributions. And luckily, when we applying the KL diversion to normal distribution, there are some formula allow us to compute it because every normal distribution has two parameters. That is the mean, and this is a covariance metric. So if we know what the mean is, what is the covariance is, then we can use these two parameters to compute the value of KL diversion directly. So that's the idea. However, the interesting thing is that if we want to actually derive the formula of the if we want to derive the formula of variational long-haul encoder, we are beginning or start with nothing like an autoencoder. We can consider the generative model directly and try to solve some technical issues along the way. And finally, we are going to get something similar to autoencoder. 好，所以它有这边我们等一下介绍这个过程，它有趣的地方是我们一开始其实并没有特别的想要去做 autoencoder，虽然刚才我们已经先把它的结论先说了，它其实就是很像一个 autoencoder 的东西，但是多了一项，以结果论来说，它中间多了一项去确保它的那个 z 很像一个常态分布，但是在这个过程之中呢，我们可以用另外一种思路去得到一样的结果，但这边的过程其实一开始我们并没有一定要做 autoencode，我们只是想做一个生成模型，但在做这生成模型的过程中，我们会解决一些困难，然后用一些方法解决这些困难，最后得到一个很类似于 autoencode 的东西，就是我们刚才讲的那个东西。So along with we are going to introduce some mathematical formulas. This is probably the only time, or I will go into the mathematical details, mostly about the computation details for the formulas. Later in this class, we are going to talk about in this course, we'll talk about like diffusion models, or like other flow matching and other models. We are still going to talk about some formula, but probably I won't go into too detailed technical details about how these formulas are going to compute, but they are pretty similar. Every inequality has its reason. So we can derive the inequality one by one. 所以之后这次大概是我会讲比较详细的地方。那后面很多类似的diffusion model 或其他的一些东西，有一些类似的东西，我可能不会讲的一条一条的讲那么详细，但是它的过程其实很类似的。就有一些上下界啊，或者是你去做的它的一些思路是很类似的，但是因为东西比较多，所以我这边当做一个讲的比较详细的例子。因为我觉得这样比较平衡一点点啦，因为毕竟一直讲这个东西怎么推导的，会有一点点无聊。而且这东西so if you want to really understand mathematical formulas, it is better you understand, I mean, to read the formulas from the paper or derive it in your own hand, because that is going to be more interesting. if you just listen to someone explain to you the formula one by one, it is kind of boring and um I mean, if you do it on your own path, it is sort of fun or like an interesting procedure or process to understand the formula one by one. Although it may take some brain muscles that you don't use that often. So in some cases, you would get stuck at a certain, uh, I mean, from Formula One to Formula Two, to Formula Three, you may stuck on at some steps. That's for sure. Even if you are very familiar with mathematics, it is still possible. You got stuck in some step. You don't understand how from Formula One to get to Formula Two. But I think recently because we have some AI like ChatGPT or things, so you get some tools to assist you. So in the past, you probably have to ask people why Formula One why we can derive like equation two from equation one. And if you got a lot of blocks between like step 1 to step 100, you got like 10 or like maybe 20 or maybe 80 steps you don't understand, it will get very tedious and difficult. But luckily, I can imagine that. But luckily, we got AI, so um, maybe AI can be a assistant tools for you to understand how these formulas are derived. But one thing I can sure is listen to someone to explain. I mean, for every formula you see in a paper or in a textbook, if your only source of digest or understand this the right process is from listening to someone else, it is very boring. Even if you have the ability to understand or to read the formula yourself by yourself, listen to someone to explain the step one by one is kind of actually very very boring. So I think the right dose or thing is okay. You see a couple of examples and learn how to read the formulas one by one to get the ability to read the proof or a calculation. Then you will read it by yourself. OK，我刚才其实简单的说，只是说，当你要看这种比较复杂的一个式子推导的时候，呃，我觉得为什么我这边只有这边会讲比较详细，是因为有一件事情，就是你可能会觉得说，我自己读那个式子的推导其实很困难。就比如说它中间有100步啊，可能我们一般来说可能会碰到2、3步有困难，然后要花点时间去，也许是上网找一下，也许去问人，可能是这样。那只有2、3步嘛，但整体来说，可能100步以后有90步你可以过得去，然后有几步你不清楚，问人，然后甚至你100步看得懂就过去就会可以。当然我可以想象说，如果你中间有80步你都看不懂，这件事情很痛苦，所以你会觉得有可能会觉得说，我这种东西只能听别人讲，一步一步讲完。但事实上是，如果你这种东西听别人一步一步解释的话，其实是一件非常痛苦的事情。其实是一件非常痛苦，就是你就算是有办法去读它，也不能说痛苦，而是无聊啊。因为，对啊，就是它整个过程是在一个被辅助的状态之下，就好像你跑步可能是还不错啊，可能跑完之后你感觉还不错，但是如果你每一个步就是别人帮你一步拉一步拉，这是一个比喻啊，就是帮你的脚往前抬、往前抬、往前抬的时候，这件事情其实很无聊，因为你不晓得干什么，这件事情不晓得它的目的是什么啊。当然，如果你跑步的过程中，可能有2、3个地方跑不过去，有人帮你推一下，这个是过得去的，可能还中间大部分时候还蛮有趣的。但是如果说，比如说，我可以想象中间，比如说你有100公尺，大概你中间碰到了大概50次、60次需要人帮你往上推的时候，或者往前推的时候， 你会觉得很麻烦啊，这是可以理解的。那还好现在有 AI 工具可以帮你做这件事情。但是如果说你要，就是说有 AI 工具推，这是一个解法了。然后或者是说你有10个地方有问题，那每一次找人问，或者这也是个解法，但不好不方便，这可以理解的。但是有一个是绝对不行，就是我刚刚讲的，从头听到尾这件事情，因为就算你有能力能够跑，然后你这件事情从头听到尾，除非中间你已经大概，比如说好了，从头听到尾只有一种情况，就是你大概已经看过一遍，但是你中间卡了4、5关，或者是卡了10几关，也许多一点点。那你在听的时候发现你卡关的地方被解释掉，那这是可以的。但一般来说的话，从头你这件事情是从头听到一个解释到尾的，那其实是极为无聊的事情啊，不是说它本身那件事情，我觉得本身是不可行的，因为它太过无聊。好，那我们这边就开始解释它的内容。我刚才只是在说明说为什么我只会讲这个地方，在这个地方讲比较详细，后面的话大家会简单带过去，因为那个太过无聊。好，OK, so let's begin to explain how we derive the variational autoencoder formula. Start with something nothing like an autoencoder. Uh, at the beginning, we will considering a generative model in general. What is a generative model? We have a latent space and a parameter theta right here. So this is the parameter we wish to train our model, and z is latent. We wish to generate something, so it is a function. F z z theta. Theta is something we are going to determine in the training process, and the z is latent. And the output is an x. Our goal is to make the x to have a distribution similar to the distribution we get from the data set or something we wish to have. 好，所以它的基本构造是我们有个 FZ theta 是你机器学习或者你神经网络头的模型的 parameters，Z 就是你的 latent。那 Z will have a distribution that is predetermined like a normal distribution or other non-distribution. Our goal is to make sure that the generate hit thing because Z is a random distribution. So X can be considered as a random variable depends on Z. Our goal is so that this distribution X is similar to something that we observe from the training data set. So how do we measure to check we are already success or to measure how success we are 所以我们要怎么去确保说这个 X 跟那个真正的那个我们生出来的东西跟真正的那个 X 的东西很像。So let's say you can see that we can use the likelihood maximum likelihood sense to check how is our how close is our generated sense and the actually distribution. So we use the maximum likelihood formula. So this one is the maximum likelihood formula. So we integrate the sense over z because z is our primary distribution, is our latent, which is a linear random distribution. So this is the formula of the maximum likelihood. If we are considering the X is the data set itself, I mean the training data set itself, it will be something like, suppose we have a data set like X1, X2, X3, da da da. This one is going to be something like summation I and P xi z theta. Okay. and P Z D Z. Okay, so if it is discrete, we can use summation instead of the integration. But the basic idea is that we kind of compute the likelihood of the observed data by using our model. We are going to change the theta because theta is something that is not yet determined. But our goal is to find a theta to maximize this likelihood. Okay, so what is Px z theta? How do we actually model these things? Like, if you can imagine it, we have a neural network. How do we actually compute these things? PZ is quite easy because if we are going to use z normal distribution as z. So z PZ is in fact just simply the standard normal distribution. So we know what PZ is, but what is Pxz theta? So one way to do that is that we are model it as a normal distribution. But like we said, the normal distribution has two parameters. One is the mean, and the other is the covariance matrix. So we are modeling this one as modeling this one as using like a neural network. And about the covariance, we can see there are different ways to do that. We can also use another we could use another like a G Z theta to generate our covariance matrix. But in general, we wish to make things easier. So a lot of time we simply use the we are assuming them to be independent, and we use a predefined sigma right here. You can see that we're assuming it to be constant and independent, and there's a hyperparameter sigma that is predefined. 好，所以前面只是说那个我们要算的东西是 maximum likelihood，那你可以一般来说我们的资料集是有限多个，你可以直接用 summation 去算就可以。虽然这边写的是积分，但是我们观察到那个东西，那我们要最佳化的东西就是 theta 让它最大。那 PZ 的话，因为我们已经知道 Z 是，比如说它是一个标准的常态分布，所以 PZ 我们完全会。那这个东西是我们需要模型自己去做，毕竟这边还有 theta 跟你模型有关的。那一个常见的做法就是，好，因为我们就用 normal distribution 啊，我们希望它有点像是常态分布这个东西，跟常态分布有关的。可是呢，我们模型的部分在什么呢？因为常态分布会被两个东西决定，一个是它的那个 mu 嘛，就是它的 mean 那个东西，一个是它的那个 covariance matrix。好，那 mean 我们就很单纯的用一个神经网络，比方说 f， 因为你还是要 z 要当做输入嘛，然后你的 theta 就是它的中间的 parameter 参数，你就输出它的一个 mu 出来。那后面这一串呢，你当然也可以用一个 g 什么 z theta， 然后输出一个很复杂的一个矩阵。但是一开始我们都会用比较简单，而且事实上大家也是用比较简单的。这边就很单纯的用它是一个对角矩阵。对角矩阵还有很多方式啊，就中间你每个东西还是可以变化，但是它用最简单的，这边都是0嘛，中间都是同样的一个常数就这是 i 嘛，然后一个固定的变异数乘上去，一个固定的 variable 乘上去。好，所以这边假设就是个别是独立的，然后我们只要输出一个 mu 就行了。好，那 so to be precise, let me give you an example so that you can understand what it really means. I mean, if you can read this formula, this actually says a lot of things very clearly. 所以你要是不熟悉的话，你可能刚开始看到这个式子会觉得这到底在讲什么？但是它其实讲的非常明确。我们so f we are assuming I mean f could be any model, but since we use neural network a lot. So let me just give you one example. We could use like a neural network. It could be convolutional neural network, could be like just an MLP, and if you wish to use transformers, that could do it. Let me just call it a neural network. So suppose we are going to generate things like an MNIST dataset image. So for example, MNIST is a dataset that considers a lot of small image like 28 by 28 and like digit, handwritten digit like 3, 4, 7. Oh, this is MNIST dataset. You probably have already used it before because in our, at least in our autoencoder example, in a homework, in a homework and example, there's a facial MNIST and MNIST dataset. So let me just use this as an example. So what does it mean by this FC z theta, and what is the relation between this n and this distribution? The thing is, we have given any z, we are training a neural network. Let me just call it f. F is a neural network, and we are going to get something. Something is fz theta, of course, because theta is a parameter here. This thing is in fact an image 28 by 28 image。好，所以什么这个 FZ theta 是什么呢？如果我们的目标是要生一个 MNIST 的图片，那事实上 FZ theta 很单纯的就是生出一个28乘28的图片，就像你的 AutoEncoder 做的那件事情一模一样。哦，因为它只是，但是它只是一个 mean 啊，因为我们等一下还要做一些让它随机的事情。哦，就是说我们的随机性除了我们的 latent， 当然 latent 会变之外，哦，但是另外还有一个，他这边想做的事情就是，我们每一次生的图片，即使我们的 z 确定了，而且 theta 已经固定了，然后 z 确定了，我们还是要额外增加一些随机性。但它本质上跟原来 AutoEncoder 的那个 decoder 很像，我们给你一个 z， 它就生出一个28乘28这个图片，它可能长得就是像是这样子。好，但是为什么要加上这个呢？这个的意思就是我在它这边28乘28嘛，所以有一大堆 pixel。每一个 pixel 呢，我把一个 pixel 拿出来。This normal distribution sense is in fact just saying that, okay, after we generate this image, like what we do in a decoder, we do using a decoder in an auto decoder setting. Auto encoder setting. After we generate this image, we are going to do some extra procedure to include some randomness. So one thing to do that, this actually says that for each pixel, we are trying to plus some random variable to it. That is like because this is for just each pixel. Because the properties of normal distribution, we can use this random unbiased, the mu is 0. If we plus something, it will become this normal distribution. So this is in fact, if we read these things, it is in fact saying, okay, let me first generate the mu, which is fz theta, which is image right here, and we add some noise into it. The noise is pretty much simply independent normal distribution, which we apply to each of the pixels independently. That's it. Also, the whole procedure right here, described right here, is that, okay, we generate an image, and we, for each pixel, we independently add some noise to it. So what is a noise? The noise is a normal distribution. you can consider the mean is 0 and the standard deviation is sigma。所以这边其实它做的事情就是，你可以想象，就是我们在生出那个图片之后，我们再加上一些杂讯上去而已了。那这杂讯它这边告诉你的意思，只是我个别的点。这个 I 就是说，你看到 I 基本上就是说，每一个 pixel 我独立去加它，我独立去加它。那要加多少呢？就加一个 normal distribution。这个 mean 我们前面已经弄了，所以这边 mean 已经对消掉，这边还有一个0在这边。那它的 standard deviation 就是 sigma，就这样子而已。我们每一个 pixel 上去加一个 standard deviation 是 sigma 的 normal distribution，当做杂讯加上去。So later on we are going to kind of explain why we need less noise. Because the obvious question is, okay, why we need to add some noise? The reason is that if you don't add the noise, you are essentially adding something like, equivalent, you are saying something like sigma is equal to 0. If you don't add any noise, you are kind of considering something like we are adding a noise, but the noise has a standard deviation 0。好，你这边第一个想的是，我们为什么要加这个杂讯？就是看起来好像没什么理由嘛。那其实你不加杂讯，也可以把它看成是加一个杂讯，但这杂讯它的标准差是0，这也是一种方式去看它。So if you do so, if you make the sigma to be 0, and which is equivalent to not adding a noise, it will introduce some technical difficulty to compute the maxima likelihood. The reason is that if you don't do that, and because our neural network, although it's pretty good, it can output anything similar, very close to any goal you wish to achieve by the universal approximation theory. However, it is just an approximation. It is not exactly equal. So if you do not add some noise right here, it will introduce some issues because it will make this one to be 0. Because we are only approximating it, so they are not equal. Even you make the standard deviation to be 0, it cannot. You probably cannot find a z to actually hit the sample in your dataset, in your training dataset. So you will get something like a 0 right here. Then it is very difficult to optimize our model because it is a hit or miss. So if it doesn't hit the sample directly, you're going to get a 0. However, if you introduce some noise, even if you not hit the sample directly, you're going to get something because if they are close, they are not yet just hit the sample, but they are very close to the training sample. It will get something because this one is more smooth. So if you are very close to the sample, you'll get some probability and you'll get some reward in your maximum likelihood. 好，所以这边我们要说是，你如果不加的话，会出什么问题？如果不加的时候，你的问题是说这个东西会变成0。原因是因为我们的神经网络比方说以神经网络来说，你的东西真的要打到你的 sample 的时候，其实不容易。我们有一个叫做 universal approximation theory， 就是你的神经网络在一些条件之下，比如说你有一个够大的 hidden layer dimension，你可以逼近任何的东西，任何的函数或任何的东西。但它毕竟只是逼近啊。那我们一般来说，你的经验也是你的神经网络只能，你要真的完全打到某个东西，其实有点困难，要100%一模一样啊。比方说 MNIST 来说，就是那个，你看每一个数值可能都是一个浮点数嘛，它每一个 pixel 28乘28 784个 pixel， 每一个浮点数都一模一样，差0.0001都不行哦。那这样子它才会算是中如果你不用这个，稍微有点把它 模糊，有点像把它模糊化放宽一点点的话，它一定要中了这个东西才会中，因为它只有中和不中嘛，你就打到那个点才是一嘛，然后不打到那个点就没有中。哦 ，normal 有点像是一个圆圈，哦，慢慢往外扩散。但是如果 sigma 是0的话，就是一个点，它的想象中就是一个点。那你的目标如果在这边的时候，它就没有分数，就是中和不中而已。那如果你是一个有一点点 sigma 哦，它有你就算不中的时候，差一点点，它就会有分数。哦，所以第一个原因是，就是这个东西，当然首先就是它很可能全部都是0，根本没办法做。你再怎么做都会差一点点，基本上实际上都会差一点点，它永远都是0，根本没办法做。再来就是这个才会连续嘛，啊，你才有办法去做，比如说我们 gradient descent 啊什么，你才有办法去做微分去弄到。所以我们这个算是一种技术上要做的事情。好 ，OK， so this is that we can use introduce some randomness after we generate the images. You can consider this way. We introduce some noise. There are some benefit so that we can technically we can do the optimization more smoothly and easy. However, this is not the only way to do so. We can also use a binary distribution as well. Then in this case, we still generate something like this one. Let me move it a little bit higher. Normal distribution is not the only choice. Another choice is to use the binary distribution, which means that we still generate fz theta, and it is still something like 28 by 28, things like this one. But we're treating this one as a probability on each of the pixel. So each pixel we are going to interpret its value as a p, which means it has a probability like p to be 1 and the probability p to be 1, which is if this image is something like this one, the white part usually corresponded to the higher value, and the dark pixels are corresponding to the lower value of each pixel. So we'll consider it as a random distribution. So each pixel, we are going to generate something depends on this distribution. And this distribution is going to be either 1 or 0, but we have the probability of each pixel. Each pixel is still independent, but the value it indicates the probability of it being 1, and 1 minus p of the probability of being 0. So it is a binary distribution, either 1 or 0. I will consider kind of like this one. And our output is corresponding to the probability. 好，所以这个东西其实它做的事情是我们一样，如果你要用 binary 的话，它意思它通常是这样做，我们一样是让它输出一个28×28，只不过每一个 pixel 上面的值对应到其实一个几率，这个几率就是有点像我们丢铜板一样啊，kind of like a coin flip. We get the probability right here. 好，所以我们得到这个几率，然后它就是这东西还是会随机，你生出来之后，我们还是会随机再生一个图片出来。啊，每一个地方它要不然就是0，要不然就是1，然后依照的几率就是你这边 pixel 得到的值。啊，所以你这边这个 pixel 上的值，我们希望它0到1中间了。你的要是输出一个什么2啊或者-1，那这个就没有意义了。好，所以每一个东西其实都是0到1中间，你可能要用 sigmoid 或什么。好，所以它还是中间后面会变。那这样子的话，还是可以让我们去计算像 likelihood 的这些东西，只不过它后面的这些 likelihood 就会变得比较像是用那个比如说是 cross entropy 啊那些东西去计算它的几率啊那些东西，因为取 log 之后像 cross entropy 那样子。 好，那你当然也可以用其他，但最常见的就是 normal distribution 或者是 Bernoulli 这种零或一的几率的。当然如果是在 MNIST 的话，因为它中间值不是只有零或一嘛，它有的时候是就是介于零或一中间的值就是不是全亮也不是全暗的，所以是不是适合这件事情就有一点点就适不适合用 Bernoulli，你可以去讲啊，当然，但是因为 Bernoulli 本身它的设定的话，就是我的东西就是只有零或一，它是离散的嘛，零或一就是零，要不然就是零，要不然一。我这边只是输出它的几率。所以 Bernoulli 是不是能够直接用在 MNIST 上面？因为我们资料不是只有零或一但是你其实也可以把这个原本的 MNIST 的那个每个 pixel 的亮度，把它看成是一个几率，而不要看成是零或一，那当然也是可以用了不过这就是看你用什么工具都可以只不过你一定要用的一些几率的东西，原因也类似前面的，就是你不用这些几率的东西，你很难100%打中。好，那如果你这边有个 P 嘛，即使是你猜错了，但是至少1减 P 的几率，它还是可以得一点分数所以它这个东西会让它有分数。但是如果你不用任何几率性的话，它不完全中，你不用任何几率还是一个几率，只不过这个几率就是集中在一个点那这个集中在一个点这种几率就是中或不中，那它会很难做最佳化。Okay, so anyway, you can use any different distribution after you get something. Um, but you most of the time you need to introduce some randomness in order to make this thing actually optimizable. Okay, so the basic idea is something looks like this one. Our Z is a standard normal distribution, and we use some procedure. Mostly likely, specifically, we're considering use this kind of thing or Bernoulli things. Most of the time, you can simply consider this situation. 所以看起来很抽象啦。这边我们讲的是比较抽象的一个状态，就是给你一个 latent，它经过某个程序得到一个 x，这个当然有 theta 在这边了。但实际上你现在心里想的，只要想这个就行了或者加一个 Bernoulli 但大部分情况下，你就是说，好，我现在生上一个图片，这虽然讲的很抽象，但是我生出个图片，然后图片上面加一个杂讯，而且杂讯还是很简单的杂讯就是每个点独立的，而且一模一样的杂讯，把它加上去。So although it can be applied to a kind of general situation, more abstract in a more abstract way, most of the time we were just thinking about uh, this model, this specific model, like using normal distribution, and if you wish, you can assume this one to be a neural network or considering a Bernoulli example. So the convention, I mean, at least for me, when thinking about this kind of thing, we are trying to think it as general as possible, but keep in mind a real concrete example. And if our idea is too general, we will introduce some restriction on this general idea to include these two. I mean, in this case, we have two examples, right? To include these two examples, and to make it less abstract, so that we can move on to the next step. 所以这其实是一个我们在考虑抽象问题思考的时候的一个过程。我们想的时候是尽可能让它一开始变更最抽象的情况。所以为什么我们明明心里想的其实是这个例子，还有 Bernoulli 这个例子，但是呢，因为这个例子很简单嘛，就生一张图片，然后上面加杂讯而已，然后就生一张图片，这个图片代表是它的几率而已。那为什么要搞得这么复杂？这是一般的一个样式因为我们一开始的时候尽量让它更一般化，但心里想的其实这两个例子，但是发现它走不下去的时候，我们再把它这个很抽象的东西，它稍微变得具象一点点但是还是包含这两个例子，但是让我们的东西可以继续推导下去。你等一下会看到有一部分是在做这件事情。好，比方说我们当然也 ，for example, we might wish this z to be any distribution, not just the little I, but if it makes things difficult to actually to derive the next step, we are willing to assume it to be the situation, so that Z is going to be the normal distribution, the standard normal distribution. Because the key idea is to make things easier to think, even when we consider the abstract case. It is just because by thinking it in a more abstract form, it is easier to think, because we can focus on less conditions or less. We won't be distracted into too many spatial cases. We only need to focus on the most general form of the in the question. 所以我们随时都会想要可以让它变得更简单或更抽象。其实它的目的都只有一个，就是让它的过程很简单。你会觉得说，这个推导很复杂或干什么的，没有错，这东西都是很复杂。即使你再熟练，它都是很复杂的。那我们之所以会用抽象一点的，或者是在抽象的时候，随时让它变得不抽象，都是要让它更简单。抽象其实也是让它更简单，因为你只要考虑比较简单的 case 考虑比较简单的状况直到这个简单的状况不合用了，我们再去，因为我们重点只是让它推出来，然后你如果把它变得非常抽象，有它的一些好处啦，但是那是后来的事情。一开始的时候，你如果只是要解决你现在的问题，你随时可以把它变得不抽象，因为重点是让它可以推导下去你后来发现抽象也可以解的时候，你再把它回过去，再去第二次处理。但是这些的重点，你要知道这些看起来很复杂或干什么的，它并不是为了要把它变得让你看不懂，它其实都是为了要让这件事情容易做所以你在中间过程我们会发现做不下去，我们就会引入像这种，比如说好，我们现在已经知道它是这个样子了嘛，那这边是超级抽象的，什么东西都不知道，但是在这种情况能够推下去，我们就推嘛，因为它比较简单。那推到不能推了，我们再引入这个东西，比如说我们到时候可能会需要去计算 K divergent 计算两个 distribution 中间的 K divergent。那一般的 K divergent 你很难算可是如果你假定它是 normal 的话，你就算得出来有点像这样子。Okay, so first of all, how do we choose Z? We at this step, our intention is to, okay, can we just simply assume or convince ourselves we don't need to be too generalized? We can simply assume Z to be the normal distribution, standard normal distribution. In fact, can we simply assume that? The answer is yes. The reason is that no matter what the distribution Z you choose, it doesn't matter that much. Even if you choose Z to be like a normal distribution like this one, by changing the model, changing the theta, you can actually, changing the F, and you can do anything. So no matter what the Z is, like if we wish to, if our X is a distribution like this one, like a ring, doesn't look anything like a normal distribution, right? Because this one is kind of like a piece without a hole, and this one is kind of like a hole. They are topologically different. But even in this case, we can contrast some mappings to map this one to look like this one. So the argument is that no matter what the distribution Z you choose, it doesn't matter. We can still construct a formula, a mapping, to map to any distribution. So the standard normal distribution is just as good as any other distribution. So we can fix it to be a standard normal distribution. 所以这个的论证其实就在说你这边可以固定一个啦，因为反正你不管固定什么，我们都可以把其他的distribution模拟出来。那以这边来说的话，它是去对应到这个环，原因是 不是因为这环简单，而是它在本质上面，它这边想要用这个例子，是因为这个例子是一个看似难的东西哦。因为如果你要把一个没有动的东西对应到一个有动的东西，在拓扑上面是不可能的。如果你把它看成是一个形状，它是一个圆圈，这是一个环的话，它没有连续函数可以对过去。但是因为我们是 distribution 啊，然后我们只要看大致上相近就可以了。所以实际上你是用这种方式，它这边还是有一个 randomness 在这边但基本上就是 z 除以10加上 z 除以 z 的那个长度，它 randomness 在这边。这个东西它如果 z 的长度是0的时候，它会爆掉。但是大家那个你要达到0的几率也是0嘛，因为它只有一个点而已，所以它根本不在乎这件事情。那其他的地方的确是可以对应到它，等于说它不连续的，它是一个不连续的映射也是没有错的但不管怎么样，它本身就是说，它这边只是要说服自己，我这边可以先固定下来，用一个常态分布、标准常态分布。毕竟后面的东西用模型去训练都可以办得到，它不会让我损失东西。好，so the first answer is yes, we can simply choose the simplest one, like the standard normal diffusion. Okay, so how to, I mean, the reason we wish to answer this question is that if the answer is no, I mean, if if the answer is otherwise, we cannot simply choose z to be an standard normal diffusion. Then since it's going to be getting complicated because we probably have to determine what the distribution we want to choose for first. It will make things really, really complicated. So that's the things that we wish to confirm at the beginning. Okay, so that's the easy part. The difficult part is the second part. How do we actually to calculate the integration over z? Because like this one, we are going to have to compute the uh, integration. We'll have to compute the integration. The thing is that computing integration is quite difficult. A naive integration is something like this one, like what you have learned in calculus, like a Riemann integral. We are using a partition and to approximate the integration. 所以你可能在学微积分的时候学到这个东西，就是我们做积分的时候，可能用这个方法可以近似的去把它积分出来，近似去把它积分出来，可能中间取一点像这样。So in calculus, you probably have learned the Riemann integral like this one, like in the definition of in Riemann integral, and we can actually find a partition on here to find the integral. It is in fact the way we do the numerical integration. Though we may use some more advanced formula to make it converge faster in certain condition. Our general idea is we have a partition and to approximate the integral by this summation. This looks simple, like okay, anything seems to be can be done pretty easily by using a numerical approximation. However, this integration is for one dimensional. If you want to do like a two-dimensional integration like this one, and this is the z-axis, we have some function looks like a surface on here. If you wish to do so, you need to, like here, we might separate the part. We have a partition of size of 1, 2, 3, 4, 5, 6, 7. If we wish to do this in 2 dimensions, our partition might be something like this one. Okay, so in x-axis, the size of partition is 7, and in the y-axis is 7. So we can have the same accuracy and precision for the approximation. But in this case, your computation cost is kind of grows really fast like a square. You need to have a partition of size like 49. And this is only for two-dimensional things. I mean, if we want to make it more accurate, the approximation more accurate, our method is probably just to make the partition more finer. 所以我们想要让它算得更准确，通常就是让它切得更细嘛。Like we have a partition of a size of 100, 1,000, or 10,000. If our domain, integral domain, our domain for integration is simply one-dimensional, the cost is linear. The cost is linear. If we want to get the partition to be like 10 times finer, we need to have a 10 times computational power, because the size of the partition is going to be like 10 times. However, if we are working on a two-dimensional space, if we want to make the grid or partition to be 10 times finer for each axis, we are going to have like the size of partition is going to be 100 times bigger. So if we are consider the space for image, it may look something like 28 by 28. It is 784, or like a higher resolution things like 1024 by 1024. It is almost the dimension of also like 1 million. So even if we are using a very, very small partition, I mean, we divide each dimension to be like 2 parts. And if you have a dimension like 784, you probably are going to have a 2 to 784 size of your partition. 所以即使你把说我每个维度就分个2个就好了，就取2个东西去做。那你要是有个784维度的东西，你最后的大小是2的784次方。所以so your summation is going to be something like I is from 1 to 2 to 784. That is very, very huge, and you have to divide it by something like this one. That is, your n is a very, very huge number. Even if you do a it's extremely low resolution things. 所以即使你用一个非常低解析度的东西去切你的 domain， 它的那个计算量也是很夸张了。But of course, our dimension is smaller, much less than 28 by 28. Because as we say, as in AutoEncoder, our dimension of Z is much smaller than the dimension of X. But still, even if you just have a dimension of like 32 or maybe even 10, then if you wish to have a more resolution in your partition, it is going to be huge. Like even if your dimension is something like 32, your dimension is 32. If you wish to have a resolution of like 10 at each axis, your partition is going to be like this huge. This is a huge thing if you want to run the integration over it. Okay, so one question is, do we really need this kind of accuracy? Can we just use like a Markov, Monte Carlo sampling things? We don't need to like 10 to 74. We just randomly put like 10,000 samples, maybe 1,000 samples, and hoping the Monte Carlo method can do it for us. So what is Monte Carlo method is something like this one. This is our domain. We don't do a partition. We simply put random samples in it, and this is domain. This is a domain. and our function is on the z-axis. So we can use Monte Carlo method, right? 好，所以说好，我们也许就用蒙特卡罗嘛，反正我们没办法切那么细，我们就随便丢一些 sample 然后算。就像我们其实我们用那个 stochastic gradient descent，其实也是某种程度上也类似，反正就是随机丢进去，有点像蒙特卡罗这种方式。However, there is no free lunch, so you could do that, hoping the Monte Carlo will solve things. But by using a random sampling instead of like a grid or like more designed sampling, it's still doable, but you cannot expect it to be more accuracy or more efficient than a grid setting. So you are going to sacrifice the precision, although it is easy and it is no it will work on most of the situation without any assumption or condition. It will the benefit of using Monte Carlo is it does not require too many assumption like the smoothness of the function or anything. But you're going to sacrifice the precision. 蒙特卡罗它的优点是它不需要任何的，它需要比较少的一些前提的，它就在你的任何情况之下，它这样丢下去，它都会有一定的准确度。但问题是，就比方说你用什么梯形法、辛普森路什么东西的话，你可能会需要一些那个你的函数的一些性质，它的一些平滑程度。当然它会更准确。那蒙特卡罗它不需要很多，那它有一些它的准确度的一个下界，但是它准确度上升就不是很快。So you can use Monte Carlo, but you are going to sacrifice. It won't get too many precision. 好，所以因为它是随机的丢进去嘛，它跟你比起有设计过的东西比起来，你总不可能说好我，因为你看什么，你就是每个 dimension 你的 resolution 就是切两个，那2的什么2的32次方，2的或者10的多少次方，如果那种东西，比如说切2个，你觉得解析度太低了，但是要这么多 sample， 那怎么可能你随便丢，比如说只要丢1000个 sample， 那它这个东西看起来就会比较好。在2维的时候你看起来不错了，因为2维你这个你要切成100份的话就10乘10嘛，那个比如说这个解析度看起来还好，那你丢1000个进去，它其实看起来很多了。可是问题就是高纬度的时候，这件事情它其实很sparse 的，所以它其实不会得到很高的精确度。好 ，so this is just called the curse of dimension。这就是那个什么维度的诅咒这件事情了。Okay, so maybe we don't need that kind of precision. I mean, we simply just use a Monte Carlo style things to randomly put like 10,000 samples. Although they are kind of sparse in a high dimension, but probably we don't need that kind of precision. We can just kind of approximate it and to train our model, and it can in fact make the things I mean, still can train our model to a reasonable result and make it works in practice。所以会不会其实我们反正就先不管嘛，它也许精确度不高，我们就丢进去做，那最后模型还是可以训练出来，因为很多时候是这样子。However, we can argue that we need quite precise and quite high precision in order to solve this case. This is because you can see in this image, the first one is 2, is probably from a sample. You can assume this is from actual sample. This one is kind of like 2, but this one is broken. So this one may be less desirable. And the C part, the most right one, the rightist one here, is more desirable because it still looks like a 2 and very close to this one. So in perceptionally, we will say the C is more close to A. C is more close to A. However, if you use a mean square error, which is going to be pretty similar to the likelihood sense if we are going to use the normal distribution. You will see that this one is B has a very is a smaller mean square error comparing to the C. Suppose our target is A. 所以我们其实你可以看出来，我们可能比较想要最右边这个 C 的情况。假如 A 是 sample，那我们其实比较想要 C，但是 B 的话，因为它的 C 的位置跟它有一个小小的误差，所以看起来比较像，但是实际上它的 mean square error 比较大。那 mean square error 其实就跟那个我们等一下，如果我们用那个 normal distribution 那个，我们前面不是有 Bernoulli 跟 normal distribution，normal distribution 那个其实基本上就是一个加上一个常数的大小的变化的那个 mean square error。所以你看到，如果我们要去用算那个 mean square 那个 likelihood 的话，那它其实就算 mean square error， 差不多就算 mean square error。那你会发现这两个的 mean square error 很小，那这两个很大。So that means we are going to need a lot of sample to make it works. Otherwise, the model will think this one is B is more similar to A. To solve this, we need a lot of samples so that we can find I mean, if you have your training data is just huge. So we probably can find instead of A, we can find a sample that is similar to C, similar enough to C. That can solve the problem if we have a huge sample. But otherwise, it is we're probably going to need another way to measure the similarity between these kind of images. 所以如果你有大量的 sample 的话，这件事情其实问题就不大，因为这个东西有变嘛，但是你的 training data 可能资料真的超级多，就像我们说那个什么10的什么784次方类似这种东西了，那你可能就可以找到一个跟这个很接近的东西，那这个就不是问题了，因为现在的问题只是因为这个东西是好的，但是因为我们的 sample training data 数量没那么多，所以跟它最接近的可能也就这个，但这个东西会更接近，那这件事情就有点糟糕了这件事情就没办法达到我们要的东西，所以要不然我们就是要把那个 maximum likelihood 把它丢掉，或者用其他方法去算它，不然的话你直接用简单的方法去做的话，你需要很大的 sample，不然就不能用同样的方法去衡量了，你可能要别的方法去衡量说，这两个还是很像 ，A 跟 C 比 A 跟 B 像，不然的话你没办法生出，因为我们其实基本上你要生出像的东西，你就告诉我的模型什么时候做对的，什么时候做错的，但是如果你用刚才比较naive的方式的话，其实没办法的。OK， 好。So how do we actually to solve this issue? We still need a good sampling, but if we do the naive sampling or just doing the Monte Carlo sense to kind of okay, we just do it randomly, it is not good enough. So how about we are going to use a more precise or like a more intelligent sampling, because for most case, PXZ is nearly zero. 所以另外一个解法就是好，我们还是做 sampling， 但是我们不要乱枪打鸟，或者是说就是像 grid 这种方式去做。我们可不可以做这 sampling， 但这 sampling 做的非常的聪明的方式去做，非常精准的去做，因为大部分的 PXZ 都会很小，小到接近0。那这个接近0的话，差不多可以忽略掉。因为真的要靠近的话，就是说你真的要那个让它不是0，它只有它的每一个 pixel 基本上都只能差一点点，因为它就是 mean square error 嘛，所以它每一个 pixel 它能够差距都一点点，可能这边稍微亮一点点，这边稍微杂讯一点点，它才会有一个足够大的那个 likelihood 在那个地方。所以其实你就是任何找2张图啦，比如说这边是一个1，就是即使在资料集里头，这是一张1，这是一个2，这2张图的 likelihood 都会超级小。所以重点是，即使是我们已经设计好最好的模型了，就是这个 Z 能够已经跑出来非常像那个图了，我们每一个图 我们可以就是这个每一个 sample training data 的时候，每个 sample 我们都可以找个 z 让它已经非常像了。那即使这样子，在这种情况之下，你也不是随便一个 z 它都会跟它很像，它只有少少的力会跟它很像，所以它比较正常的状况会是像是你可以想象的状况就是我们很多 z。Suppose so the situation is more likely something like this. In this data set, we have suppose we only have 3 data, like 1 or 2 or 3, just 3 data in a MNIST data set. So even though in this case, suppose this is our z, it's kind of like a normal distribution, but uh, we let's just use the because I don't want you to think about this one is less likely and this one is more likely. Let's just consider the uniform distribution. So even though in this case, it is more like we have a z1, we can generate something very similar to this one. And we have a z2, generate something very similar to this one. And z3 generate something very similar to this one. So if you're comparing this one and this z3, you still get something likelihood to be really, really small, almost 0. So the best scenario is something look like this one. The Z1 match Z2, the Z1 match 1, Z2 match this image 2, Z3 match this image 3. For other Z's, like this one is in the middle between Z1 and Z2, it is probably, the PXZ is probably 0 for all zeros. For all X, in this case, we only have 3 different X. But it can generate new instance. And if this one is very close to the U1, like Z1 plus a little optional, this one probably get something similar to this one and will get something non-zero. But for more of the zero, I mean for most of the Z, if we fix an X for most of the Z, you are going to get something very, very close to 0. So how about we just choose the pair of xz that really matter, because we already know the most pair of x and z are going to be 0. So we don't need to actually calculate. We can just estimate their value because they are not matter. They are not relevant. So if we can do that, if for every x we can find a z that is more relevant, that is potentially has non-zero value, we can do the desampling of x and z pairs to be more efficient. Probably we can solve the issue. 好，所以我们的大部分状况就是有点像这样子，因为你其实虽然说这个最好的状况就是某一个 z 会跟这个 x 很像第一个 x 很像，第二个 z 跟第二个 x 很像，第三个 z 跟第三个 x 很像。但其实在这种最好状况，它大部分的 z 你要随机取一个 z 和随机取一个 x， 它们的那个 pxz 还是都是0。那既然我们知道大部分都是0的话，我们只要再估计它一下就好了。只要把它真正非0的地方挑出来，如果我们可以非常精准的挑出这些 xz 来做积分，然后剩下用估计的，这样是不是就可以解决它了？ Okay, so that's the idea. We're trying to sampling it more smartly, not just randomly like a Monte Carlo, or like brute forcely like just like we do the Riemann integral. We're doing it smartly. For each x, we probably can pick some z that is most possible, potentially has non-zero likelihood value. So let's call this smart sampling procedure to be Q. Okay, although we have P and Q right here, P is stand for like computing the probability. Q is they are not symmetric. Q is our procedure, specifically for our like given X, like an encoder. The Q is going to become encoder, and the sum of P, I mean this P is going to be becoming a decoder. Given by given, this this thing is going to be the decoder, and this one is going to be the encoder, because this one is given x, we find a z, and this one is given z, we find an x. But the notation is not symmetric because p is used in a lot of different places like px, pz. P is standard for like the notation for probability. So I'm just saying that this notation is not the best choice, but you have to kind of notice about that. Be careful about that. But anyway, if you see the pxz here, this one is eventually is going to become the encoder part of the things, because this one, I mean decoder part of the thing. Because this is pretty much saying by given z, and we are getting x, the model of given z, and we are going to generate x. And this one is eventually going to become the encoder. This, although the original idea, the motivation is we want to sampling it more efficiently. But if you really think about it, considering the x and the z pair things about that, we're actually trying to find a construct an encoder, because we already know that each x we can only find one z. Although, I mean, from the motivation, it just a distribution. It doesn't say anything about okay, every x we find a code z. It just saying okay, we construct a distribution so that in this distribution, we are if we're sampling our z for each x, if we're sampling z from this distribution, it is going to be more efficient for our computation of the maximum likelihood. 好，所以这边只有一个有趣的地方，就是这边虽然概念上是说啊，我们只是要找一个 distribution 这个 z，这个 z 呢，是只是一个 distribution 啊，所以它可能是一个分散到很多地方的东西。但实际上，你从刚才的东西，你大概可以猜到我们心中想的那个 case，其实比较像是每个 x 对到一个 z，所以它比较像是一个 encoder。哦，只是说你在一开始我们的动机的时候，其实比较像是，哎，我只是一个抽样的过程。哦，但是你从刚才的例子，其实大部分我们其实心里想的具体的例子，其实就是我的每个 x 对到一个 z，所以当后面需要的时候，比如说它模型要出来的时候，我们会毫不犹豫的把它变成那个比较特殊的 case。但想的时候，一开始想的时候或计算的时候，还是可以到目前为止还是可以直接把它想成只是，它也不需要一定是一个 encoder，它可以就是一个一般的几率分布而已。Okay, so suppose we have this kind of smart sampling things. Can we actually use this smart sampling things to replace the original sampling? I mean, just discard anything outside of the smart sampling because they are almost zero. Almost certainly they are zero. Can we just simply do that? It has some doubt. It kind of like a long tail things, although other things are almost zero, but they are a lot. Our sampling is very efficient, which means it is just a very, very tiny little portion of the whole domain. So all the other things not in our efficient sampling is going to be as a huge amount, although their likelihood is close to zero. But because of the long tail effect, can we simply discard them? We don't know yet. But we can estimate it. 好，所以现在第一个想法就是，好，那我们既然有这个 sampling 了，我们直接把这个 sampling 当做我们的 z 的 sampling 方式，我们可不可以直接的就把这当做我们算的值呢？但是不见得可以哦，因为其他东西虽然接近零，但是它东西数量很大，有点像长尾效应这样子。所以它到底能不能呢？我们可以算一下嘛，我们可以算一下。Okay, so let's denote the K divergence by D, and recall that the two this is definition that I going to if you are not familiar with K divergence, so this is a formula of K divergence to just recall a distribution. Suppose we have two distribution Q and P. The Carroll divergence here. This is just a definition, and you can see that I use the different D. I don't know. I think the same D, but we swapped the P and Q right here. Let's make a little bit inconvenient, but this is just a definition. If we Carroll divergence is not symmetric, so DPQ and the DQP is not the same. Okay, so but the formula is it's pretty simple. It looks like this one. We'll integrate over the distribution of P, and to estimate, like you can see that it is duly to do the calculation over P, we simply over P. But we are measuring the difference between Px and Qx, log Px and log Qx. So if P and Q are the same, the distribution, the density function is the same on each of the instance, then this is going to be 0. So this is quite a straightforward way, or like easy way to measure the differences between two distribution. There are many different motivation about the Carroll divergence, but currently I'm not going to talk about that. So if you are not familiar with Carroll divergence, just you can just think this is a way to measure difference between two distribution. We measure the difference for each point, and we integrate over the whole domain respect to the distribution of P. We have to choose one distribution to do the integration, right? Expected value is actually just the integration, like this one, the formula right here. But anyway, this is definition. Okay, so let's compute the our goal is to QZX, but in order for the sake of the simplicity of the notation, we put a QZ here. But keep in mind, we are trying to compute the QZX difference between QZX and the PZX. But if we write the QZX every time, it will make it a bit longer. Okay, so I forgot to tell you thing. The most of this stuff is come from the second one, this paper. This not I mean, this is a tutorial on variational autoencoder, which is a recommended reading for everyone, every student. I wish them to study for variational autoencoder. So I should put it in front of everything. The material in this note is basically following this tutorial, and the above one is another tutorial, which is also pretty good. But in this note, we are following the second one. So these formulas are taken from the tutorials, and in the tutorial, it is using this formula. So this may not be ideal. The only reason I can think of is that it is for the simplicity, for the sake of simplicity of the notation. But anyway, QZ is kind of QZX is a special case of QZ. You can think about that. So these formulas are also works. But what we are trying to do is to measure the difference between QZX and the PZX. That is what we are trying to do. So we are because we are wondering what is the difference. Is this a good approximation? So we are first measuring the difference between the QZX and the PZX. Because if PZX is something like a correct answer, But anyway, we are measuring it using the KL divergence, and let's compute it. So by definition, this one is the expected value respective to the diffusion of Q here. And we also further simplify the notation from QZX to QZ, and here we only to Q. But this one is actually QZX。所以我们这边其实符号有点省略啊。这个 QZ 其实我们心里想的是 QZX，只是这边先省略。那这个 Q 其实也是 QZX，只是这边都省略掉。但是我们这边只是在算 KL divergence，用后面这个式子。So we're using this formula, but just replace P by QZ and Q by PZX, and we got this formula. Okay, so then we can use the Bayes rule, 就我们贝氏法则 ，PZX is equal to PXZ times PZ, divided by over PX. So why do we use this one? This is because the Bayes rule is kind of a very popular tool that we frequently use. And another thing is that because we are more interested in the encoder and the decoder things, and the PXZ is the decoder. So it makes sense to compare it to the decoder. And we already know what the PZ is, and PX currently, because we are thinking about we are working on the training data. So PX is more like we choose things randomly, uniformly from the training data. Okay, so this makes a lot of sense. And this is probably another reason that we don't use the log QZX instead of just using, we use log QZ instead of using QZX. It's because, okay, if we are using Bayes rule right here, why not use the Bayes rule applied to Q? So that may make some confusion. But the reason of using this is that QZX is already in a form that we are interested in about, and the PZX is on the wrong direction. So we are making it to the correct direction. And plus, this is a multiplication and division, which works pretty good for log because we can separate it in a summation way. So let's do this and replace this guy with this guy. And we get, okay, we still get the log QZ because let me use the pen right here. Okay, let me move. So we still got the log QZ here. It's just a copy here. We don't change anything, modify it. And this guy is going to replace by this guy, and this guy. So this is log PXZ. And we still can minus log PZ. And because PX is independent to the Z right here, we can move it outside from the expected value formula to get a log PX right here. So this is one small step to simplify the formula because we can isolate log PX outside of the expected value. And we can further simplify things. Observe that DQZPZ is this guy. So we're picking up this guy and this guy. Now, this is not a surprise because, yeah, we kind of separate it into different terms. So we can choose two of these terms together to form a KL divergence. So if we pick this one and then this one, we can kind of use the KL divergence notation to kind of shorten the representation. Okay, so these two guys become the KL divergence. We have a log PX right here. So log PX, and the KL divergence of what? This guy is QZ, PZ, so it's right here. This formula is a little bit confused because it swapped the right hand side and the left hand side. So you can see that is to be here. So if this one is on the other side, so the sign changes. Because this guy minus this guy is the QZ, PZ, but we change the sign to the other direction, other side of the equation. So we get a negative sign right here. And also we keep this guy. Although here it is a negative sign, but it is actually moved to the other side of the equation. So it becomes positive. And finally, we have this guy here. And we keep this one. But it is also moved to the other side of the equation. So it from the positive to the negative. So this is the formula we got. And finally, we substitute this QZ by QZX. Then we get this guy. Because our intention is to compute the difference between QZX and the QPZX. So we change everything here and we got the final formula like this one. Okay, so now you can forget all the process and focus on this formula. So what does this formula says? The first part right here is the likelihood we wish to compute. If we are trying to, we want to maximize the px. Because this px is in fact the error. I mean, it's a maximum. It's a likelihood thing. We want to maximize the log likelihood, and the second part is the differences between QZX and the PZX. That is the differences we initially wish to kind of try to compute. We didn't actually compute it, but we start by writing this formula and do a little bit of computation. But anyway, this is something we are intention our to make it the difference to be small. Are trying to train our model, encoder and the decoder both, to make this guy to be small. But this one is mostly for the you'll see that this is not originally, it is not our objective, but currently because we move it to this side, we are going to optimize the first part log px for mean most likelihood and the second part altogether. So these two is going to become our new objective. 好，所以最左边这是我们一开始设定的 maximum likelihood。那这个地方呢，是我们假设它应该很小了，我们应该很小，那所以我们要让它变很小，所以变成我们的目标的一部分。所以最后我们其实我们现在变成要去最佳化这个东西，要让它这个东西变大，整体变大。那整体变大的同时，它必须这个也大，然后这个变小，后面这一项变小，所以大的减小的它才会变大嘛。就最后变成这样，最后这变成一个额外的我们。从最原始我们只要 likelihood 的嘛，但是我们因为引入了一个有效的那个 sampling， 所以我们也同时的希望这个 sampling 变得更有效一点点，会跟真实的那个情况是更一致的。Okay, so this becomes our new objective. We want to maximize the local likelihood and minimize the error of our efficient sampling. But since we want to use this formula, you can imagine that, you can guess that we are not going to actually using the left hand side. We are using the right hand side to do the actual work instead, because that's what the equation for. If we maximize the right hand side, it is the same as maximize the left hand side. 好，所以接下来我们要做的是右边这一串，我们希望把它变得最大化。我们希望我们比较能够算，因为左边这一串这两个东西不是我们可以算完，因为6个 PS 本来就是我们没办法算的东西。那这东西我们刚才导半天了，也就是弄出一些关系。好，但不管怎么样，就是只要这个东西的差距很小，我们差不多这个右边这个东西就跟这个值差不多。所以这是第一个解读。第二个解读就是我们只要想办法把它变大，那你的 log px 至少也跟它一样大，因为这个东西是一个 Taylor divergence 一定是正的。所以我们虽然没办法直接最大化它，但是我们把这个最大化，尽量把它变大。那我们可以确保的是 px 至少大于等于右边的。So there are different ways to interpret this formula, this equation. So one way is that because the left hand side equal to right hand side, so if we wish to maximize the left hand side, we can simply maximize the right hand side. We are hoping that the right hand side is easier to compute because we already know that log px is our original goal, which is difficult. We are already argued that it is difficult to compute it naively. So we are hoping the right hand side is easier to do the computation. Another way to interpret this thing is because Taylor divergence is always non-negative. So we know that although this is not the original objective, but we know that log px is greater or equal to the right hand side. So we can, if we are trying to maximize the right hand side, we are going to ensure that the maximum likelihood is at least the value we get, although we don't know the exact or likelihood rate value of the likelihood, we can sure that it is at least the value we get on the right hand side. So the question is it easy to compute the value of the on the right hand side? So a first observation is it actually looks like an autoencoder, especially for the first term. You can see that the first term pretty much means you read from the ZQ here. We get the Z from Q, which is because Q is in fact QZX. So it means, okay, we randomly choose one X from our training data and running the encoder and we get a Z. So this means how the process of picking up a Z. So this one actually means that we randomly pick an X from the data set, from the training data set, and we apply Q on it and get a Z. So this process is ZQ. So this is doable. This is doable. This and this is finite because our training data is finite. So this is doable. And we can actually compute log xz because what is log pxz? This is we first compute f z theta, and then we plus some small random noise on it. So this is the pxz. I mean, this is the x prime, and what we will do. I mean, this is the x how we generate the x prime. But what is it meant by pxz? Because we know our distribution is in fact. Let me put it again. We already know our distribution is something like n f z theta. And we know how to get the z by using the process we described before. So this is our distribution. Given a z and for a current theta, this is our distribution. This is our distribution. And because we know the original, what is x is? So recall that we pick x first from the dataset and doing the applying Q encoder on it and get a z, and then apply the f to get this distribution. So we know what the x is. So we simply compute the density of x according to this distribution. According to this distribution. Because this is a distribution, we can compute anything, the density function of anything according to this distribution. 所以这是我们已经得到这个常态分度啊。我们等一下只是要把这个 x 带进去里头，去算它的那个密度函数，这样就可以了。所以这是算得出来的，而且整个过程是我们知道怎么做的。So this is computable. Everything is computable, and we know how to do it. We simply do the procedure we just described. We pick a random x from the data set and applying Q to get a z, and applying the f to get this distribution. And we compute the density function and take a log. That's all. This is pretty doable. And we can compute the empirical expected value just by randomly sampling the x from data set. So that sounds good. And it actually looks like an autoencoder. The Q encoding x to z, and the P decodes z to x. So right here, we are already thinking that Q to be like an autoencoder. But how we actually, I mean, right now Q is still a kind of abstract model. So what the Q actually is when we do how should we actually write the model or build a model to actually produce the we also use a normal distribution like here, but instead of using a fixed constant simple covariant metric, we are using another neural network. In our case, we use another neural network to generate the covariant matrix. But we're not considering the general covariant matrix. We are only consider a diagonal one. So we are the mu is, so we are using two. You can consider this is two neural network. The first one generate like suppose our latent dimension is 32. 所以假设我们的 latent dimension 是32. The mu actually take by taking any x. If we consider the MNIST case, this is a 28 by 28 image. We put it in the model, then we get 32 number. Then they are corresponding to the mu. And we get another 32 number. And we are putting it in a diagonal. You can see that it is constrained to a diagonal. So we are not using a constant standard deviation, but we are still consider this matrix to be covariant matrix to be diagonal. That is, every two variables are still has no covariant to each other. They are also independent to each other, but their values are dependent on by a neural network. And we have 32 values right here, and all other values like covariance are 0. So each of the 32 components have different mean and a different standard deviation, but they are still independent. So this is the setting. So of course you can think about another situation that, okay, why they have to be independent? Can we simply construct the a more general covariant matrix, like we generate everything else, like 32 by 32 elements? Of course, they have to be like symmetric. So we have like only about half of the parameter that is useful. But still, this is one option. And another direction is why should we generate this kind of why cannot we just simply use a constant standard deviation? Can we simply use a wilder? I mean, can we just simply generate the mu itself and then fix it to be some predefined constant? You can try different things, but we are trying to fix on our setting on this one. Other things are all reasonable, but if you want to make it more complicated, it will make the computation more complicated. If you want to make it simpler, it is possible that this model is not power enough to make a power enough Q. So that because you can see that our where depends on that QZX is very close to PZX. But anyway, those two approaches are still reasonable and worth try, but they are two different. I mean, we have a choice right here. And currently we are focusing on the choice as the standard one. This is almost every, if you see almost every variational autoencoder things, it almost do the same thing like this one. 好，所以这边其实是一个选择啦，就是你这边这个 QZX 要怎么选？那这边的常见的选择就是我有个命，这一定要啊，这32个不一样的，然后反正你一定要打到不一样，不能这个要打不一样啊，就是你 AutoEncoder 嘛，你可以想象那个一定要打不一样的东西。但是随机性呢，这是随机性啊，你可以像前面一样那个用一个 sigma 然后 i 啊 sigma 平方 i 这样子固定住了也可以啊，或者只学一个 sigma 也可以。那它这不是，它整个那对角线每个地方都可以不一样啊，这是标准的做法。你如果觉得说这个东西不够，然后把它扩展，那也是合理的啦。只不过这个是标准的做法，大家都是这样做的。Okay, so this is Q. So we actually already get everything about to compute this part, the first part. We already get everything that we need to compute the first part, including what the Q is and including what the P is, how the P works and how to compute log P XZ, all of them. But you can see that there's almost no loss function to help us to determine what the sigma is. I mean the sigma in a model of Q. So we need more. This is simply the autoencoder loss. We call this autoencoder loss. Later on, we're going to actually compute the loss. So you can see that if we are using the normal distribution as the output, it will very similar to mean square error. If we are using the binarial things, it will kind of like a cross entropy. But what about the second one? How do we compute this one? DQZX and the PZ. So first recall that because we are using QZX like this one, and the PZ is in fact the probability of Z, which we already know that PZ is just the normal distribution 0, I, and the QZX is a normal distribution of this guy. So we can actually compute the KL divergence of them using the parameter mu sigma here and the parameter 0, I here. We can simply do that. Okay. So what is the formula to compute the KL diversion between two normal distribution? This is the formula. This is the formula. So if we got a mu0, sigma 0, and the mu1, sigma 1, first we compute this trace. The trace is a summation of the diagonal. And we compute this guy and this guy. But recall that the one of the mu is 0. Like this one. One of the mu is 0. And one of the sigma is in fact I, which is I1 here. So this one, although this looks kind of intimidating, but because it has an inverse, but recall that this one is just in the identity metric. So you can actually eliminate it totally because the inverse of the identity matrix is just identity matrix, and identity matrix is a unit in the matrix multiplication. So we don't have anything about it. And because mu1 is simply 0, so we got the mu0, which is mu here. So like negative mu0 t times negative mu0, and 2 negative make it a positive. So we got this guy here. And about the first trace, similar thing here. We can totally eliminate the sigma 1, got only the sigma 0. So this is just the trace of the sigma here. And then we get here the log determinant of the sigma 1 and the sigma 2 because we only need the denominator. The numerator is just log I, which is 0. We can eliminate as before, and we get only the sigma x here, the determinant of the sigma x here. But because it is in a denominator, we have a different sign, negative sign here. So that's all. This is the second part. Because we use the normal distribution, because we choose to use the normal distribution. So this thing can be computed quite easy. You can choose other distribution as well, but you have to use a different formula. So basically, both of them can be easily calculated. The first one is simply the auto. You can consider it as an autoencoder loss because it is the encoding and the decoding process, and we are computing the log density function, log likelihood. And the second part, you can consider it as the variational loss, the variational loss, which is used to ensure that QZX is similar to the normal distribution. So each of the QZX is similar to the standard normal distribution. Because we are calculating the KL diversion, we're making it optimize. When we maximize this, we're hoping this one to be as small as possible overall. Okay, so we got most of the formula down here. Okay. Oh, this is a trace. Okay, so to put everything together, this is our objective function. We put it like this one. The things inside the expected value here is the things that we have seen before, like here. The left hand side. Okay, so we put the expected value to emphasize that, okay, we are actually compute them over the data set. And the following is pretty much the same. The autoencoder, here is the autoencoder loss, and here is the variational loss. And we can do this by using the stochastic gradient descent way, or you can use Adam W to unlist these things. So how about how to compute the autoencoder loss? What is the exact formula? We already got the exact formula for the second part, the variational part, because this is the formula. But we still got two different choices of this log xz, log pxz, because we have two variations that keep in our mind. One is the normal distribution variation, and the other is to make it a binomial. So recall that the pxz theta is this guy if we are considering the normal distribution, kind of adding a normal distribution noise. You can think this is our output and we are trying to add some noise right here. The log xz is in fact this guy. The reason is that the formula of a normal distribution we can pick the multivariate normal distribution. The PDF that is a density function is looks like this one. It has some constant right here. You can see that it has some constant. This is simply some constant. And because our sigma is a constant, so this is a constant. And this is a mean square error part. And this one is I because we are using an I and the sigma square thing. So this one is just the square error and the exponential right here. But we are taking a log. So this one becomes plus some constant. And because we are taking log, we're only getting this guy. So this is essentially just x minus mu square. Oh, so this is mean square error. That's why we get a mean square error, because the log density function, because we have an exponential here. So we cancel out the log and the exponential. And because the exponential part, exponent part here is simply a square error. So we are actually getting something like a square error. Plus some, I mean, we still got some constant right here there, but basically this is just a square error. So let's go back to here. So that's why this is just x minus f z theta, because this is, if you recall the formula, this is x minus mu, and our mu is f theta. So this is why we got the x minus f theta. And because if we are using the I itself, then it is going to be a little bit simpler. But because we are sigma square right here, so we got a sigma square here, and plus some constant, and we are not bothering to compute. This is because the when we make a differentiation, it will come. But this C is whole bunch things right here. If you want to calculate in a more accurate way, you can still calculate this thing. But the sigma is just the big sigma is just the sigma square I. So you can compute the determinant and actually find the constant. And this is 2 pi and the dimension. Okay, so about the binomial case, this is going to become things like this one. The fz theta is the probability. So this comes to be the log. It's quite easy because the probability is like p power to x and 1 minus p power to 1 minus x. And if you take log, it will become the cross entropy. This is a binary cross entropy. So depends on what your stochastic model, your random model distribution, you can compute this kind of thing according to your formula. Everything can almost everything can be replaced because we actually doing the more concrete calculation a little bit later in the later phase. So you can actually replace the the Q thing to another distribution if you wish to, which you will see in the VQE layer, the VQVAE layer, and you can or replace this distribution like a normal one or binary one, or maybe you can be more creative. As long as the log density function is easy to compute, you can use anything you want to do. Okay, so about the actual implementation, there's one thing called the reparameterization trick, which is essential if you want to do the implementation. It's quite of a straightforward. But in order to discuss why this is actually a thing, let us first imagine an implementation that is very difficult to do. Quite of straightforward, but difficult to actually implement. So the procedure we discuss is, okay, we taking an X from the data set and put into X to a Q, right? And we get mu and sigma. Okay. And we have to sample Z. That's what we were saying. We have to sample Z from this guy, this normal distribution, and send to we got a Z, right? And send it to a decoder. And finally, we get a FZ. And for the loss function, we calculate the KL divergence here and the mean square error here. Of course, we plot some like a scale things in here. But basically, we have a mean square error, the autoencoder loss and the variational loss right here to compute the KL divergence between the standard normal distribution and the normal distribution we compute from the Q. However, the red part is difficult to do that because, so what is this layer exactly? Do we need a normal distribution layer? Can we actually do that? Imagine that we have a linear layer that is just do some arithmetics, and we have like a convolution layer, a transformer layer. They are always has some operator that we can define, and we can do the differentiation. But what does it mean to, okay, randomly sampling something from a thing? What does it really mean? So it's kind of difficult to imagine what we can have a layer called normal, and we get things from that. Instead, we kind of isolate the random part from the like the mu and the sigma part. So instead of feeling this as a one thing, we are trying to sampling an epsilon from the standard normal distribution right here at the beginning. This is independent to the mu and the sigma. And we are not trying to do the the gradient on this guy. It doesn't really matter because it doesn't affect. If you are using a back propagation, there nothing go back to. It is irrelevant to the mu and the sigma. This is something we wish to training. And of course, it is irrelevant to the FZ. We only need to train FZ and mu sigma. This is the things that we are training. This one doesn't need this one. Aside from we want to construct the input for it. But when we do the back propagation, it has nothing to do with it because it is in front of it, and it doesn't have nothing to do. It has nothing to do with that. So we don't need to worry about the, the how to compute the gradient for sampling things. We simply and treat it as input. This is quite a common way to do that. We treat the randomness as an input, like a latent or other things. Okay, so we treat this as an input, and instead of sampling z directly from this guy, we multiply. We use this formula: z equals to the mu x times epsilon. No, plus epsilon times sigma x. So the distribution of z is the same distribution as the distribution on the left hand side is identical to the distribution on the right hand side, because the right hand side has a mean mu x and has a standard deviation sigma x. So you got the things you want. Okay, probably you need a square root because this is a covariant matrix, so you probably need to scale it. But we got what we want. So this is the whole implementation, and you can also do some generalization, like adding some condition to the variational autoencoder. Let me check. Okay. Suppose you have condition x right here. If you have an additional condition, let me check. Okay, if you have an additional condition, you just put the condition information, somehow put the condition into encoder and decoder. So your encoder and encoder can be used to decoding or encoding using the information of the additional condition. Also, then you got a conditional generative model. So currently, if you're using the diffusion models like stable diffusion or flux, or maybe like a video diffusion model like Hunyuan or Wang, one is the newest one, the most trending one, just released I think last week. But anyway, all of these models are condition model, condition on text input, text prompt. So you probably are familiar with what the condition model can do, and also other model like control net or like text to image adapter or IP adapter. They are all sort of conditional generative models, but typically for a text to image model, we're considering the input to be the text prompt, which in here, what is the X4? You can consider this is a text prompt, and Y is a latent. Now we're using the latent to generate the things, and Z is a latent here. But you have to send the information of a condition into the model and use this condition to guide the generation. So instead of just one, theoretically, instead of just one generator and or one encoder and one decoder, you are having a family of encoder and decoder, depends on the condition. Okay, so there are several implementations that you can find out, but this information is kind of outdated. You can check the TensorFlow or like Keras or PyTorch. They probably already have a lot of the code and tutorials on how to use the variational encoder. So here are some hands-on practice in previous years, because we are more focusing on the image generation. So this is one of the homework. but I think it has already been like 2 or 3 years. I'm only present this homework as a practice, hands-on practice that you can practice by yourself. I'm only limit our homeworks to be like 5 in each semester. So I'm lift this quota to other homeworks that I think is more important. But still, this one you can try. Find any code and to see how this thing could happen. So like what you do for a MNIST, for autoencoder, you can do that for VAE as before and try different dimensions. And also you can try a very small dimension like 2 dimension. Like the mu has 2 dimension and the sigma has 2 dimension. The good thing is that you can actually visualize every generated things on your on this platform. I mean on this square. Okay, by the way, what we were talking about the curse or dimensionality is probably not always applied to the MNIST case if you are using a dimension of 2. Because for this 2-dimensional things, if your latent is just 2 dimension, you probably can still use like a grid to actually to do a computation because the dimension is relatively low. And the VAE in fact can allow you to see that we can actually encode the MNIST into a rather low dimension, like a 2-dimension thing. 好，所以如果是在我们前面虽然有讲那个维度的诅咒嘛，但是其实 VAE 可以帮你的维度压到很小，压到2维。在2维上面，其实你真的还是可以做那个积分，你可以这边切个1000份，这边切个1000份，然后可以做到，你可以试试看那个东西哦，因为那个还是做得到的。比如说你用1000乘1000 100万，只是它用的那个 resource 就比较多，它还是可以做到很准确的直接去算那个所有的东西，可以把它算出来。在2维的时候可以，然后你用 AutoEncoders 不容易压到2维，但是 VAE 很容易。这个就是它其中压到一个方式，而且你可以视觉化它的整个效果，因为它就是一个 normal distribution，所以你完全可以，你看我这边就是0嘛，这边也是0到多少多少的地方，你完全可以视觉化它在这个 normal distribution 它怎么去做变化。So there's a popular visualization of what can be generated or latent space of the VAE because VAE can use a rather low. It's much easier to make the latent dimension to be rather low. So if you have tried the homework for autoencoder, you probably will find it is kind of difficult to use like a dimension, like the bottleneck dimension to be like 4 to do the autoencoder. But it is typical. I mean, it is not too bit difficult for a variational autoencoder to have this kind of visualization. This is just a standard exercise. You can get something like this one. But like autoencoder, variational autoencoder is tend to output image is kind of blurry. So you will see that although this looks pretty amazing and the pattern seems to be very good, but the things that you can complain is that the generated image is sort of blurry. And another thing is when we try a generative model, we wish two kind of things. One is it can generate something that high fidelity, that is generate something looks like the sample, and we wish it to sort of generate things that to be more creative, that generate new novel instance. The variational autoencoder is kind of blurry. So this is because we are using the mean square error. So in a way, it is used to very close to the original sample. So the fidelity is actually okay because we are using mean square error. So in the sense of mean square error, it is kind of close to the original distribution. But the creativity is a little bit low. It can do some interpolation, but it will have a hard time to generate new or novel or surprising image comparing to like again or maybe like diffusion models. So that's some characteristic of a variational encoder or autoencoder things. 这个 VAE 或者 AutoEncode 它其实有个特性，就是它可以差值做很不错，也就是说它在它可以让你的那个你可以做到了，一定可以做到的事情，就是让我 data set 你可以找到一个 Z，data set 每个 image 都可以生得出来，那它可以做出还不错的差值。那 Variational AutoEncode 可以做出更低维度然后更漂亮的差值，但是它的创造性会偏向比较不容易，比较不足。它虽然有点糊，刚才讲它会比较糊了，但是也是因为我们用 mean square error，所以它的真实度倒还好，因为我们本来就是用 mean square error，那 mean square error 就是会糊。那它的特性之一就是它比较不会生出太创新的影像出来，它比较像是差值啊。但另外一个角度就是，如果你的目标就是让它生出差不多的影像，那你至少你在训练 variational autoencoder 或者 autoencoder 的时候，你要做到的东西，就是你有时候会觉得，到底是我没有做好，还是这个方法不行？这种东西能够一定做到的东西，就是我的 sample，我基本上都可以把它，就是我 training data 的 sample，我都可以把它生出来。我都会找个 z，然后这个适当的 z 就可以生出那 training data 的 sample，而且看起来超漂亮。但是它很可能就是你用个就是中间这个 z 啊，主要就是你看像这个6可能很棒啊，这个5可能也很不错，但6跟5中间的可能会有点破掉，那5跟8中间可能会有一个模糊的东西，所以它的好坏，真正的好坏，你要讲到好坏啊，第一个就是你 sample 可以生得出来，第二个就是我们会希望中间做两个图片中间做差值的时候，它中间都还是合理的图片，而不是一个我们不希望的东西。好，但是如果你连比如说整个这个很常会发生，就颜色整个错掉了啊，或者是说你生出来的根本就跟东西不像，跟你的那个要训练东西不像，而且你甚至找我全力 data 的图片，你想办法，你随便去调那个 z，你还是生不出来全力 data 的图片，就是你 encode 进去再 decode 回来，东西都长不一样啊，那这样就不行了啊。就是 auto encode 至少能做到，就是我找一张真实的图片啊，更好的状况就是在 training data 之外，但是我做 encoder 再做 decoder 回来，它还可以做一样的东西。那就好像你的那个 CO diffusion 它有一个 auto encoder 在那边，那基本上你会期待说它的东西进来再出来的时候会跟原来一样，至少很像了，不会说它可能会有一些脸啊破掉啊，什么手破掉啊，什么地方破掉，多多少少会有一些不太好的地方，画质变差一点点。但你不可能说我进来了是一个人，出来的是一个抽象化哦，那个东西就是完全训练错了。所以这个东西有缺点有优点，但是它的特性就是那样子。那可以帮助你去确定自己有没有训练对。Okay, another interesting thing is to do this kind of thing to see it product label, also product label, doing a similar thing in 2D latent. But this one is for the autoencoder that we present last week. So another interesting thing is okay, do the same thing. And because we already have a two-dimensional latent, so can you see the similar thing? Instead, it's just kind of like this one, but instead of like generate it kind of separately, I mean uniformly, we pick the things from data set, and for each category we give a different color, and to see how the different category or different class of images are occupied in in a two-dimensional space。好，所以这另外一个就是像这种图了，但是你可以在 VAE 上面试试看，好，看看它到底生的怎么样。也就是说，我们也很好奇嘛，到底真实的那些6啊，或真实的0，它是在哪些位置？Okay, so another way to say that what I was saying about the creativity is that the VAE will have a higher recall, but yeah, it will have a very high recall, but probably less precision, but it will have a very high recall. So everything in the training data should be appear somewhere on this platform, and the generated, the decoder back to the space. When you decode back the latent, it will be close to the original one because that is how it is trained. 好，所以这边是 Variational AutoEncoder， 好，所以它还蛮有趣的。那这边主要是讲它的数学，而且它在很多地方会用到。Let's go to the next topic in a real quick way about the VQVA. Okay, so what is VQVA? So first, what is vector quantization? Just a story to motivate you what the VQVA is. The stable diffusion is actually based on latent diffusion, and the predecessor of it is actually called the VQ gain. 所以在 stable diffusion， 他们那家公司他们之前做了，他们那个团体做了一个叫做 VQ gain 的东西。那它的 VQ gain 本身前面有一个 VQ， 它用的就是 VQVAE 里头的那个前段和后段，它中间用的是 gain。那这边你看到 VQVAE 中间用的其实是 Pixel C N、Pixel R N， 我们之后会讲，就下礼拜开始就会讲 Auto Regressive 嘛，会讲。但是以故事上来说，它用的 VQVA， 你在那个 Stable 用的 VAE， 它一开始的时候是从 VQ gain 那边来的，但是 VQ gain 它用的东西就是这种 VQVAE 的东西嘛。但是那个Stable Diffusion 它一开始的时候，它用的是类似的架构，但是把 VQ 的地方去掉，所以最后回到就是 AutoEncoder， 因为它已经把 VQ 的地方都去掉了。但是历史上来说，这边就是有个 VQVAE。So the VQVAE, I mean the VAE used by Stable Diffusion is actually an autoencoder that's based on a VQVAE that is used in VQ GAN, developed in the same group. The architecture is similar, except they are not VQ. So that's just a story about what the VQVAE is relevant to the modern generative models. But first of all, what is vector quantization? So one thing to think about is that you can use a discrete representation of things, kind of similar to the clustering. So suppose we have a space of different, like infinitely many different values right here, but we have some restriction that we can only use a finite vector to represent them. So one way to do that is by using like a k-means to find the k-centers. So instead of actually transmit the vector itself, we only reduce everything to the center. So everything is just finite. 好，所以这 VQ 这件事情有点像是我把我一个向量，它可能就无穷多个在一个向量空间里头。但是某些原因，我们可能只能够用有限多个东西来组合，有可能是硬体上限制，有可能是一些等一下会讲的一些其他东西。好，但是技术上做得到啊，就是说我们可以用 k-mean 就好了嘛。好，那 k 你可以自己定啊，可能大一点，什么512、1024。但是原本的可能是一个什么32维度的空间啊，像这边是2维的。那我们用 k-mean 把我们的资料，你就可以用资料集跑，也许是中间一个 latent 什么。资料集跑完之后，我们把它缩小成有限多个，这是 VQ 这边要用的东西。举例来说啦，为什么我们有时候会限制？可能有个东西是你想要用乐高去拼一张图。So for example, if you wish to use the Lego to kind of reproduce some painting, some famous painting, you probably can only use the color that provided by the Lego blocks, or there are something called the digital paintings that you can see that in sales in some stores. 有一个东西叫什么数字化，可能从中国那边来，就数位那种东西，还有1、2、3、4嘛。 可以用不同的颜色去填它。So you can have a finite set of colors, and there's a thing that you can cut a graph that with some numbers on each component of it. Or probably it has a grid, and each small grid has a number. You can simply find the matching color to each grid, and put the color on it, and eventually, and the color has you have a finite selection of color, and each color is mapping to a number. So you can choose them to this color on this grid. This number one, I choose number one color. This is two, and I choose number two color. And eventually, if you follow the instruction, you get something like very useful, very pretty grid. That is should. Let me search it. 数字画图sort of like this one. You let me choose this one. I'm not trying to sell this. I'm just putting this as an example. So this looks pretty good, right? But you can actually do it by yourself by choosing, by following the like this one. You can follow in the instruction to each of the small part and put the color on it. 所以这个东西其实就是 filter quantization, except in this case you have a fixed set of color, but when we try to actually use on the FQVA or other filter quantization, you can create a most efficient or most suitable plate, or the set of colors that can be used in your situation, like by using a k-mean or other clustering method to find the best plate to do the coloring. Okay, so VQ has been used in a lot of different places far before like VQ again. One thing that we do is to do the color quantization, which can be considered as so this has been used a lot in early days because like in 1990s, our monitor or our graphic cards can only, or maybe like a video console, it can only display certain number, like 16 colors, 200 colors in total. So you cannot show in any color. But we can use some techniques to reduce the color to a finite set and to make this image to be resembled or as close as the original one. So one algorithm is to find the best set of colors so that we can have the minimal loss. So k-mean is one way to do that. But may not be the best algorithm. So there are also other algorithms specifically for the color quantization. Okay, so how does this quantization has to do with autoencoder? The thing is that, okay, when we do the autoencoder things, one of the issues people may have, especially for the image, is we have to have a bottleneck as our latent. 所以这个其实某种意义上来说，你可以把它看成它解决一个问题。所以 autoencoder 里头，我们常常会需要做这件事情，来去有一个 latent 在这边，然后它的 dimension 比较少。比方说原来可能是一个28乘28，我们说32乘32好了，然后可能有3种颜色，你最后缩小了之后，这边可能一个比较小的 latent，然后再放大再回来。So for example, like for an image autoencoder, it's a typical like if your original image is like a 32 by 32 and have a 3 channel like RGB, you want to encode it to a latent space and decode it back to this original 32 by 32 by 3. And as we mentioned before, the latent space, the dimension of latent space should be smaller than 32 by 32 by 3. However, a general pattern of doing like a convolutional network is to have a layer. Okay, you have 32 by 32 by 3. And then you reduce the spatial dimension to be 16 by 16. And at the first layer, you have to make the channel to be a little bit bigger, maybe like 32. So in the following, you reduce the channel. I mean, reduce the resolution, but double the channel. So you have like A by A and 64. You always do the double the channel and half the resolution. So because this is half and this is half and this is double, still this one is small, is less than this one. 因为这个变成一半，这个变一半，然后这边2倍嘛，你有一个2倍，两个一半，所以最后这个东西还是一半。So because you have two axes to become half, and one axis to become double, 2 half and 1 double. So you still the total bandwidth is still being half. However, because the first one is getting a little bit like 10 times or a lot bigger. So if you don't be very careful, like doing this one to be 4 by 4 by 128, and let's do it again, 2 by 2 by 256. Suppose we do at here. You will see that 2 by 2 by 256 is quite close to 32 by 32 by 3. This one is about 124. It is exactly 124. Then this one is 3 times 124. So technically, this is still less than this one. But like we said before, because this is image, you need to be very small. Because a lot of image, you can reduce the resolution by half and go back to the original one. They will still be pretty much the same. So the real dimension of this image is less than what it appears to be. So if you want to have a pretty good autoencoder, this one need to be significantly small. But because of this restriction, there are some difficulty to choose the architecture of this network. 所以我们其实会希望这个中间这个超小。现在这个情况来说，刚好它还是比较小。上一层的话可能就更接近一点，但这一层的话至少1024比这个3乘1024要小一点点。32乘32 1024嘛，然后乘3，所以是3乘1024。它是小了，但是我们之前有说过，图片你可能要更小dimension，因为它实际的dimension是更小，不然的话那个问题会太简单，它这个训练出来会并不是很好。所以你为了要让这个变小，那这个模型有的时候你就会很难控制，因为你如果 AutoEncode 设计到这么小的情况之下，就是它的那个 spatial 的 resolution 到这么小的情况之下，它有时候会很难训练，所以你可能会到8乘8或者4乘4就停下来，但是这边频宽就那个地方就不对，所以你整个设计会碰到一些困难。So how about if we can have a freedom to design our architecture of encoder and decoder, and without worrying about the bandwidth? So BQ is one way to solve this problem. This is not only motivation, but this can be considered one of the motivation. So instead of considering designing like this one, you can freely design anything you want, like this one. You don't actually need to reduce the dimension to be small enough to be small in original one. This can be anything. This can be anything. Instead, we use another way to limit the bandwidth to make it a bottleneck. Instead of transmitting this latent Z directly to a decoder, we are using VQ to kind of quantize this latent. So you can see that we have a table. This is our limit set of like the center of k-mean. So this, we have like 124 factors. This is a lookup table. This is going to be using the machine learning algorithm to train to decide the parameters. But we have a lookup table like the k-mean centers. And for each factor Z here, instead of passing this Z directly to the decoder, we are applying the factor quantization method right here. So if you are doing for the image, instead of using just the pixel for each channel, we are using the lookup table to have a index for each pixel, just like the digital painting that the kind of DIY project we see before. So because instead of we have a floating numbers, actually a floating number of vectors. This vector may be quite large or small, large, so it doesn't matter. But instead of using this vector directly, we are giving a number, like what we do the digital painting DIY there, instead of using the original, like the latent image. 好，所以就像刚才一样，就是我们这个 encoder 啊，会得到一张画，比较小的画，它可能它的 channel 很多是没有错了，但这都不重要，没关系。我们就像前面的数字化一样，我们前面建立了，就是这边用 k-mean 什么建立了一个表格，然后每一个我们就找它最接近的那个号码啊，所以你这边得到就是像那个数字化的那个东西一样。所以我们其实没有原来的这张图，我们只有数字化的这个东西，哦，数字化的东西，然后再过去这边。那这是每个 pixel 去做了哦。当然，它在不是图片的上面，它会有一些不太一样的地方。但在图片的话，就是那个 channel 本来是一个全彩的，它变成一个只有一个像这标号这样子。So how much bandwidth does it save? If you think about, okay, suppose we have our dimension, latent dimension is, let's say, 32. So for each pixel, it will have 32 times 2. If we use like consider it to be the 16-bit, the bandwidth will become like 32 times 4 if we use 32 bits. Even if you kind of, okay, we do some quantization to it has 8 bits, 2, 8, or 4 bits. It is still like 32. Okay, if we are considering the bits, it is 32 times 16 or 32 times like 32. Depends on how many bits you are considering. In general, when we're training, we're using 16 bits or 32 bits. But to be fair, this is a continuous space. The information is probably less than that. So if the rank is, the dimension is 32, we probably can think about it. We can estimate the bandwidth is more like 32 times 8 bits, or at least 32 times 4 bits. However, if we are using a quantized, factor quantized table, even if we have 124 factors in our lookup table, that is like a k-mean, but the k is equal to 1024. Then it only has 10 bits for each pixel. 好，所以它到底小多少呢？因为你可以看到，如果我们现在的 dimension 是32，并没有很大了，因为刚才都是2倍上去的嘛，其实那个32并不算很大。 那每一个你要算多大？你算我们正常来说是32 bits 啊，训练的时候 FP 32嘛。但是因为它是连续的啊，所以我们公平一点，可能我们就算4个bits 好了，4×3=12，4×2得8，所以有128个，它的那个频宽是128。可是好，我们现在有一个还算大一点 table， 算是1024个 center 在这边，那这个东西只有10个bit。好，那这边还算是低算的，那边算是对吧？就是10个bit，所以你就按这边的那个 dimension，其实还蛮自由的，因为这边只跟它的那个 k 有关，你可以更多一点点啊，比如说2048啊4096，那65536好了，你用6万多个6536，那也不过就16 bit。So even you are using a table with like uh 65,000 things, it is just like 16 bits, which is quite small compared to the representation of a vector. So that's one way to think about VQVAE. And but there are two issues about this approach. One is how do we actually train this like the lookup table? There are different ways to do that. Actually, two major ways to do that. One is to design a loss function. So it has a loss function to the autoencoder loss function. And basically, it's just a mean square error, but we want this lookup table and the latent, I mean the model parameters, all of them contribute to the autoencoder loss. Only that we can have a different scale of, I mean, different weight of how, although they are just the mean square error, but we can have like 10 times importance on the model and only 1 time importance on the lookup table. But basically, you can use some loss function to make the lookup table to be better to reproduce the image for the autoencoder loss. 所以训练这个东西，一个方法就是反正就是用 loss 去训练啊。原则上，他这边用的是 mean square error，只不过用他做了一些小小的调整，让他们两边就是说这个东西，这其他的一些权重和他们那个 loss 都是 mean square error，但是有一些可能这边是1倍，这边是10倍，类似像这种不同的比重，让他训练，让他区隔化他训练的比重。Another method is quite easier. We are only to observe what is here, comes here. I mean, and we use the k-means to determine the centers. Also, another approach is just using clustering method. By observing the latent output by this encoder, then we can use k-mean or other clustering method to determine the center. You probably want a more progressive and more like something like a running average things to do that. So not every clustering method is suitable, but basically you can use clustering method to determine the sample to control this lookup table. Okay, this one is a little bit tedious, but not too bad. The crucial part is, okay, if we are applying lookup table to choose to do the quantization, this is a discrete process. This one is not smooth, let alone differentiable. So there's no way to do the gradient descent to do the back progression. So how do we work around this issue? Because this one is definitely not okay. It's not suitable for doing back progression. So you cannot use any like add-on, stochastic gradient or any gradient-based method. There are many ways to do that. Again, in this paper, it uses a very simple way to do that. Just ignore it. You can see that when we do the back propagation, this one is not possible because this is a discrete operation. 所以我们做那个 back propagation 这边过不去嘛，这边过不去，但不管 它这边直接让它过去，就是这边的值，因为它的 because the dimension of this guy and this guy is compatible because that the output, I mean the k-mean center is still have the same dimension of latent. It just we are discuss some information to use only a finite set of vector, but still they are compatible. They have the same size of dimension. So instead of actually consider it, we use the back propagation, bypass the gradient back to the encoder as if there's nothing happen. 好，所以最后就是简单来说，就是他直接把这个，反正这边要做一些事情，那我们不晓得怎么做嘛，我们就把这个 gradient 直接拉回去，就这样子。So surprising, it works. It actually works. It is not surprising. That's surprising because it works kind of like noise right here, and yeah, still this is not the only method to do that. But anyway, this one works pretty well. This one works pretty well. So just this code the I don't I forgot the name, like the bypass or like the go through straight through estimator of the gradient. So by consider this as the estimation of the gradient. In fact, it doesn't make sense. There's nothing to be estimate. But anyway, the method is called the straight through estimate of gradient. And to simply it just okay, this is not good. I just pretend that I didn't see it and pass the things that I get so far back to it. Also, there are other ways to do that by using like a more soft things like this one. 它有其他的方法啦，来做这种类似的东西。不过 PQVAE 是直接这样做。Okay, so that's pretty much how we train it. But however, there's still one issues left. That is, okay, why does it code the VAE? I only see an autoencoder loss. I didn't see the like the variational loss like we see in the VAE. The reason is because this is a discrete random things. Those that's in the variation autoencoder or that the KL divergence things right here, because it is a discrete things, so that loss is zero. 好，所以它为什么还叫 VAE 的原因，是因为如果你真的像是 VQVAE 那像是 VAE 那样去算它中间那个什么 KL divergence 那个东西，那因为这个是一个离散的东西，你算起来那个东西那个 loss 其实是零。所以他说这个既然是零，所以我就用带进去，所以我就可以把它叫 VAE. So that's why it has call it the VQVAE, because in fact technically this is a VAE, but because this is it is a non-smooth operation, so that part doesn't make sense in this setting, so it becomes 0. So because I can call myself a VAE or AE, I can call myself a variational autoencoder or autoencoder. But variational autoencoder seems to be much cooler than just a regular autoencoder. So technically, it is still a VAE. Just that term doesn't exist anymore. But that doesn't make this right, because this is a discrete distribution, not a normal distribution like a regular VAE. This is a discrete distribution. And you are not applying any loss on it. So this discrete distribution, when I said discrete distribution, is that imagine this one is like 16 by 16, like a lower resolution of this guy, but has a higher channel. But instead of using channels, has a discrete index of which color, or I mean which vector should we put into here. So this one is a sequence of index 啊，所以它中间的那个东西不是 normal distribution，而是一堆 sequence 在上面，但它们中间有 correlation，因为它中间毕竟还是像一个小图片这样子啊。如果你是用那个 stable diffusion VAE，它是变小了嘛，好像是8×8之类变小的，然后还是6×4又变小的，然后中间有4个 channel，它的 channel 数量是特别让它变少，因为毕竟它还是要是一个 VAE 啦，所以它 channel 就是弄到4，然后还有想办法弄到4。那如果是原本的那个 FQ VAE，它中间可以那个 channel 可以多一点，反正它用那个 FQ 方法解决掉。好，不过中间你现在中间的东西不是 normal diffusion， 好 normal 的话就是中间的话你就是 normal， 但这个东西就变成的是 normal 的话，比如说我们 channel 可能它就不是 channel， 它是一个值的向量了，但这边不是一个 normal， 它是一堆离散的1、2、3、4这种数字在上面。So it is just can be considered a sequence of index. But what is the distribution of this index? There's no way to tell because, well, you don't have the laws to make it to be like a standard distribution. And so there's no way it will become to force it to become like a uniform distribution or something else. So it will be a very strange distribution, just like the situation we are encounter when we discuss about the autoencoder. So there's another, so they have another method to solve it. They are training another model to generate these things. So they first training kind of this FQVAE model, but we don't know what the distribution of the latent is. And never mind, we train another model so we still got a data set and we got the latent. We can generate latent for all these data set. And we train another model to generate this latent. In the VQVA case, they are using pixel CNN and pixel RNN to do so, which we will introduce in the next week. So arguably, the benefit of VQVA, I mean, VQVA can generate pretty good images, but one of the reasons that VQVA does that well is probably because pixel CNN and pixel RNN does quite good job already. And the VQVA arguably is just increasing the resolution of what pixel CNN and pixel RNN can do. Okay, so next week we are going to talk about the pixel autoregressive model like pixel CNN, pixel RNN, and also like the GPT like model. 好，所以下礼拜我们就会，因为它这边中间的话，基本上就是用 Pixel CNN 去做的。你可以说那个 VAE 就是它的贡献，可能就只有在让它的解析度变高。那中间的那个 Pixel CNN、Pixel RN 才是真正的它的英雄在，也说不定。好，那不过总之中间那个东西就是所谓的 Autoregressive Model。好，所以我们可以带到下礼拜，我们会开始介绍 Autoregressive Model， 包含 Pixel CNN、Pixel RN， 还有现在最流行的那个 GPT 模型。好，那以上就是我们今天介绍到的部分。好，这边就是那个 VQVAE 能够升的，其实已经算是升的还挺不错的了。